graph is drawn without edges crossing, the edges and vertices of the graph divide the plane into regions. We call each region a face. And yes, we do include the outside region as a face. The number of faces does not change no matter how you draw the graph, as long as you do so without the edges crossing. So it makes sense to ascribe the number of faces as a property of the planar graph. Now here's a warning. You can only count faces when the graph is drawn in a planar way. For example, consider these two representations of the same graph. If I draw this graph here, which is a representation that is not planar. That doesn't necessarily mean that the graph is not planar, though. I can just redraw this graph by moving this edge outside. Those are the same graphs. Those are isomorphic to each other. They're essentially the same graphs drawn in different ways. If you try to count the faces using the graph on the left here, you might say there are 5 faces. Right? Like let's count here. 1, 2, 3, 4, and then 5, the outside. But drawing the graph with a planar representation shows that in fact there are only 4 faces. 1, 2, 3, 4. There is a connection between the number of vertices, the number of edges, and the number of faces in any connected planar graph. This relationship is called Euler's formula. Let's take a look at what it says. Hey everyone, real quick, I just want to mention that this video is a part of a whole course that I made. You can find a link to this entire course in the description below and make sure to click on that subscribe button. For any connected planar graph with V vertices, E edges, and F faces, we have that the number of vertices minus the number of edges plus the number of faces is always 2. Why is Euler's formula true? Now, one way to convince yourself of its validity is to draw a planar graph step by step. Start with the graph P2. There's P2. Any connected graph, besides just a single isolated vertex, must contain this subgraph. Now build up your graph by adding edges and vertices. Each step will consist of either adding a new vertex connected by a new edge to part of your graph, so creating a new spike, or by connecting 2 vertices already in the graph with a new edge, completing a circuit. Let's take a look at what that looks like. I'm going to erase everything real quick here. There we go. See what that looks like. So what do these moves do? When adding the spike there, the number of edges increases by 1, the number of vertices increases by 1, and the number of faces remains the same. But this means that the quantity V minus E plus F does not change. Completing a circuit, which is shown on the right, adds 1 edge, adds 1 face, and keeps the number of vertices the same. So again, V minus E plus F does not change. Since we can build any graph using a combination of these 2 moves, and doing so never changes the quantity V minus E plus F, that quantity will be the same for all graphs. But notice that our starting graph that we worked with here, we always start with P2, has V equals 2, E equals 1, and F equals 1. Oops. There we go. So V minus E plus F would equal 2. This argument is essentially a proof by induction. A good exercise would be to rewrite it as a formal inductive proof. Anyways, thanks everyone, and I'll see you in the next video.